Hi, everybody, and welcome. Thank you so much for making the time to join us today. I'm Tyra Jarbeau. I'm the Director of Marketing and Communications here at ZS2 Technologies, and I'll be kicking us off. We're doing a deep dive into a real case study in resilience. So, extreme climate events aren't distant problems anymore. They're shaping how we design, build, and even insure projects right now. And that's why we're here to take you behind the build of a project that stood its ground in the face of wildfire and to unpack the lessons that matter for the entire construction industry. We've got a really great lineup ahead, so let's dive in. No hard hats needed for this behind the build, just a good Wi-Fi connection. While we're giving one more minute to let everyone get settled, let's cover a couple quick housekeeping items. So if you're wondering, can I ask questions? Will there be a recording? Can I dig deeper? The answer is yes, yes, and yes. Make sure to drop your questions into the Q&A box at any time, and we'll be sure to try and hit them before we wrap up. You'll also get a recording of this session. And if you want to go even further into the weeds, we've got you covered, from material samples that you can light on fire to detailed case studies or drawings you want to get into. Really, what we're trying to say is whatever you need beyond today, we're very happy to support, from the spec book all the way to the job site. I am very, very excited and privileged to introduce you to the people leading today's session. So first up is Russ Jenkins, our Vice President of Operations at ZS2. Russ is a retired fire captain with over 20 years of service. On top of that, he's a self-proclaimed construction nerd who oversees everything from quoting to production to support on the job site here at ZS2. So he brings a balance of both that builders and firefighters perspective to the conversation around resilience. Joining him is Blain Cranston, our technical sales lead and project manager. Blain is actually patching in live today from Jasper, Alberta, where he's supporting the construction of a 3-story complex as part of the community's wildfire rebuilding efforts. We were just chatting before this that the timing couldn't be more fitting here as we talk about one project that survived a wildfire. Blain and an extended team are right in the middle of helping another deliver one in a community that's rebuilding from it. He's our go-to for specs, third-party testing, certifications, and making sure everything that we design and build is proven, code compliant, and ready to perform. Russ and Blain, I'm going to stop talking for a moment if you want to say hi and good morning to everyone.
Good morning,
Morning.
everyone.
Hi. Hi, Blain. How's site? How you doing so far? How was the drive out to
Yeah,
Jasper?
yeah. Everything looks great. I know the High Rock crew that we're building this with is currently tuned in, so excited to go vertical today.
Awesome. And finally, myself, Tyra, I'm your moderator today. My role is to help guide the conversation, keep us on track, and make sure your questions get answered along the way. And just a really important shout out, we're hosting this session with support from our partners at Seco Construction to take you behind the build of the Tataskweyak Transition Centre and share what really made the difference when wildfires tore through Split Lake earlier this year. So hi to our Seco partners. Really grateful to be able to tell this story alongside you. Here's our roadmap for the next hour. It's not too late to jump out. Just kidding. We will share the basics of fire, how it starts, how it spreads, and why that matters for how we build. Then we'll break down Magnesium Cement 101. This was the material differentiator on the project. We'll talk about what it is, how it behaves under fire, and why it's different from the conventional materials most of us are used to. From there, we're going to shift into panelized prefab, the method behind this project and how the system can take a project from foundation to full enclosure in days instead of weeks with fewer people and less waste. Then we'll look at the layered strategy of resilience, how those two things, the material science and the prefab, came together, because resilience doesn't come from one feature or one product. It comes from stacking fire, thermal, and durability strategies all together. And finally, we'll share and close with lessons learned for the AEC industry, what you can take from this project and actually apply on your own sites. Whether you're building in high-risk regions or just looking for more predictable performance, In other words, to take you behind the build, we're going to start really basic, and then we'll move into how those principles applied on this specific project and how they can be applied to others. Let's get into it. So construction mixed with wildfire rarely makes a good news story, but this one did. Earlier this summer, the Tataskweyak Transition Centre survived when wildfire tore through Split Lake. The footage was striking, and the story made headlines across North America. That outcome wasn't luck. It came down to smart decisions by our partners at CECO, paired with the right materials and the right methods. And it's a story that goes well beyond one building. We really can't treat events like this as rare. It's what construction is up against right now and the environment we build in today. So you're looking at aerial footage from the project site post-wildfire. This is the first time we're sharing it publicly. I'll admit, when I first watched it, what really struck me was the contrast. You've got scorched ground in some places, yet patches of green trees still standing in others. It sometimes doesn't match the headline that there's a giant blaze and nothing is left standing around it. Russ, can you help us understand what's going on here? Is this normal from from your perspective? What are you seeing? How do you dissect this?
Yeah, so a great question. We see all kinds of stuff in the media. We hear all kinds of stories. So sometimes it's scorched earth, everything's gone, or something like this. So when I first saw this video, a couple things that resonated with me, and from my time doing in northern Alberta doing forest firefighting, you can see kind of what I'm assuming is north of the structure there. It's pretty green, whereas beside the structure to kind of up a hill a little bit there, or what it appears to be burnt. Everything's burnt. You can see the gray on the ground from all the ash and whatnot. It's all about the topography, the type of fuels that are in the area. It's not that a fire is going to come through and wipe everything out. Interesting in this case, when I saw this picture, Tyra, the first time I was thinking about it a bit, and it reminded me a few things of the past. And what struck me is how the perimeter around the building's been defended very well. There's not a lot of combustibles, obviously some finer fuels with some of the grasses, but even just the gravel around it to help protect so fire can't creep up to the structure itself. Even just seeing the way the topography and some of it burned, fire creates its own weather when they're this big and as they roll through. So really you're trying to defend that area the best you can.
Thank you. I mean, building on what you've seen firsthand and how they behave on the ground, can you just walk us through the basics? How does a fire start, spread, and what do we need to understand before we even start talking about materials or that specific project? How does fire behave or heat transfer?
Yeah, for sure. There a couple of interesting things, and knowing we only have an hour, because this literally you can get into this science of this stuff and speak for a long time, but a couple neat things that actually speak to what CECO did on the project, our panels. So to understand part of that, you have to kind of go back a little bit. So it's okay, well, how does heat transfer? Important to know there's three methods for heat transfer: conduction, convection, and radiation, really. So for those that aren't super familiar with those, conduction, so that's like a frying pan. When you're cooking in your kitchen, right? That frying pan conducts the heat underneath it very well to cook whatever food you have in it. That's one way heat moves through and can eventually cause a fire. So a couple of things on this build to speak to that are pretty neat is our panels in particular don't conduct heat very well insulated. There's not a lot of thermal bridging in them. Even the exterior layer from there, you'll see in some of the pictures of the structure, metal clad siding, something that although it conducts heat well, it's actually got a space behind it, and then it's something that can't start on fire itself. So then convection, right? So that hot air around a fire, I mentioned a moment ago, how some of these fires actually create their own weather. I've been in these situations in some fires in actually Northern Ontario and Northern Alberta, where the fires create their own weather, meaning their own wind patterns. They're carrying hot air ahead of the fire, which is actually starting to pre-dry and prep that area for more fire. That's why they grow so big, so fast. So if we know that and we can help on the convection standpoint, even at smaller scale, and so an example in this building would be if this building is sealed up where no hot air can get into tight spaces and preheat combustibles, there's less chance of it burning, catching fire, waiting for that fire front to move through. And then the last one, radiation. And that's literally a good example would be the sun. When we go outside, the sun's radiation, the waves from the sun don't heat up everything around us as much as they heat up the surface they hit, whether that's our skin or a building. Same is true of a fire. As that fire front comes through, that radiation from the fire front, that heat, those invisible waves are hitting a structure and preheating it. If you have a structure that has components on it that dissipate that heat as much as possible and don't heat up themselves or heat up what's behind them, you have less chance of that combustion starting. And that's where I think our panels really shine and some of the products that have been put on this building.
So, Russ, does that mean with radiation that in fire, radiant heat could ignite surfaces even without direct flame contact? So when you're talking about that gravel line or its own weather, does that mean things can ignite despite not being in the specific flame path?
Great question. A lot of people, certainly I thought this when I was younger, would think, oh, you have to be touched by a flame to start on fire. You absolutely do not. Everything that's combustible will reach what's called an auto-ignition temperature when it gets hot enough. That means that the off-gassing, because it's really gases that burn, not solids. A lot of people don't know that. But when you look at a wood fire, it's the off-gassing of the wood. The flame will be just a little bit off the surface of that wood. It's the off-gassing. That gas is what burns. Solids don't typically burn. So that radiation preheats everything through the air, and eventually, without flame contact, a building material, or example would be people that live kind of on the edge of cities in that interface area, the wildland urban interface, and they want to stack firewood close to the house and put combustibles. Those heat up, and they reach that temperature, and without contact of flame, they can actually start on fire, and they're a great fuel source to get that building or that structure started.
Thank you. I appreciate that. Going even more into the science, we like to nerd out here at ZS2. The picture that you're seeing is clearly one thing is not on fire, the other is completely in flames. One of the biggest differentiators on this project was that smart material choice. So that's magnesium cement. Blain, can you talk me through the basics of magnesium cement technology 101 and why is it different than most conventional materials that we know of?
Yeah, for sure. So MGO cement, it's fire, water, pest, mold resistance, all of those things. Like right here, you see it compared to a traditional OSB sheet. It's non-combustible, has zero flame spread, so it performs extremely well. It is resilient. And this is engineered for the exterior envelope of a building or of a structure. It's a little different than, say, precast concrete or the Portland cement that we see on our roads. It's lighter than that as well. So overall, it performed extremely well that way. You pair that with the non-combustibility factor, and you're making some good choices that our partner Seco is able to stack on top of.
Russ, you had mentioned life safety at the beginning here. One of the things that I think is so interesting about magnesium cement is that when you pair MgO plus fire, it gives off steam, not smoke, due to all the encapsulated water, just quite literally going down to the nitty-gritty of the material science. Can you talk a little bit more about what that means when building material is giving off steam instead of toxic off-gassing and how that can help protect people and structures?
Yeah, for sure. So kind of going back a little bit, solids don't typically burn. There's a case for that with a chemical chain reaction. We're not going to get into that today. So it's that off-gassing, that preheating. So this great picture on this slide where we have a piece of OSB and our tech board beside it. And the OSB, as soon as it starts heating up, gives off a toxic gas that's also combustible. So it helps itself burn and for that fire to grow. Whereas the magnesium board, the beautiful part of the tech board, as it heats up, it releases steam. So it's chemically encapsulated water, literally, that's bonded with it. As the board heats up, that comes off as a bit of steam. That's how that heat is transferred, and why. And this exact demo is a great one, where after you turn the flame off, you touch the back of the MGO board, and it's warm, but you can touch it. We don't touch the back of the OSB sheet. Number one, your hand gets dirty from soot, and because it's too hot. So the MGO board, because of that off-gassing, or not off-gassing, but the steam that's released, it absorbs a lot of that heat evenly. And that, from a fire standpoint, means it's not giving off a toxic gas that's toxic for humans, number one, but also helps propagate that fire and gives that exponential growth to that fire spread.
Thank you both. Okay, so we started with the right material, and then a big part of why this project performed the way it did is that right material choice was paired with both the right method and the correct execution from the builders on site, CECO. So Blain, let's start with you from a really technical side. What are the benefits of a panelized prefab system compared to traditional building methods? The picture that you see, how is that different on Jasper's job site or this project here compared to like a traditional stick frame?
Totally. Anything that's prefab construction, the construction phase starts in design. And with our system or anything prefab, that's what you're doing. You're starting early, you're eliminating the variables that typically happen with stick frame or traditional construction. All that's controlled inside of a factory. On top of that, you have smaller tolerances. You can install this quicker with less skilled labor. So you're eliminating a lot of those hurdles in this situation in a very remote area. And you can optimize for that area, right? Here we see a full SIP envelope, roof, walls, and floor. So you're taking away those variables. You're left with a system that is extremely airtight, right? It has a reduction in the amount of lumber in it, by roughly 30%. So it performs well that way, also performs better from a thermal transfer standpoint. So you're in a good situation.
For that thermal transfer, Russ, is there anything you wanted to add to like those 3 C's, or really drive it home in kind of this visual comparison, how they could come into the building, or why that airtight methodology helped protect the build here?
Yeah, for sure. And it's interesting because I've been thinking about, obviously, as we build up to not just this webinar, but knowing this project when it went up, the area it's in, thinking more about our panels and some of the stuff we say about our type of construction off-site, and how we build it in the factory and make it perfect so it fits like Lego and all that, and how that works for this building. So the interesting part, so airtight. Okay, well, we know heat transfer is one of the ways is convection. So if we're airtight and air can't easily move in and out, more so than regular construction, just by virtue of our panel connection, by the way you put it together, immediately you're taking one of those transfers of heat away. The thermal transfer, so our panel, the fact that we do use in this building, it was lumber splines, but they're 48 inches apart to connect the panels, that tongue and groove connection. Those are encapsulated by the board, and there's only thermal bridging at 48, and lumber doesn't conduct super well with the mag board on it. So if you think about the way heat transfers, by virtue of just a SIP system alone, you're actually reducing all the different ways heat can transfer. Let alone then, we're just one part in that full solution. And I think what CECO did, and we'll see, and I think you have some slides coming up with it, of some of the finished product where they put the right parts and pieces on the exterior of the building so that nothing was combustible. And they have a design, because of the SIPS system, where there's not nooks and crannies. I've seen some homes in the interface before. There were old cabins that were built a long time ago, and there's all these places, little fire brands, so little pieces that pop out of if you have a fire at home and you hear the noise, and a little brand lands on the floor and you get it off before it makes a mark. In fires, those can get in those nooks and crannies, sit there for long enough, and start to smolder away, and to build and to start a fire in those combustibles. So we don't have the combustibles, we don't have nooks and crannies, we're airtight, there's no thermal transfer. reduced thermal transfer, right? None of these are, nothing's fireproof. All of a sudden, you add all those together, and you have an extremely resilient building.
Thank you. That was great. Blain, Russ just said it, but in case anyone is not familiar, what is a SIP? We can see a picture of this singular panel there, and we're showing how it goes together, but what is a SIP by definition?
Yeah, like I'll forego Russ's adult Lego block reference, but at simplest form, that's kind of what it is. So it's a structural component, and it's literally a structurally insulated panel. So you're taking interior sheathing, exterior sheathing, insulation, as well as a structural member, and in this case, 48 inches or 4 feet on center, and you're putting it all together. The way we design, we take everything, we give it a alphanumeric label so that it's easy to follow, regardless of skill level on site, the number of skilled laborers, those types of things. We plan ahead, provide those install drawings, and then you plug and play. That's how that works.
Thank you. So how does all of this get put together in the middle of a remote location? Some of these builds, you can see snow in the pictures in the dead of winter. How do those shipping and logistics work out, when we're installing panels by panels and connections? Can you talk me through a little bit of that build process, or even what you're doing in Jasper today?
Yeah, for sure. And it all boils down to that planning ahead. But the way that we manufacture and then ship the product, it all follows that same sequence of, following the instructions or the adult Lego blocks. And so, like we said, everything's labeled alphanumerically. That is manufactured for that specific panel in our facility in Calgary, right? From there, it gets flat stacked, and it gets labeled, once again, alphanumerically in the order that it's going to be installed. We then ship flat stacked, and that can happen in a variety of ways. So it could go typical freight on a truck, container, ice roads, and situations where you're going to northern remote communities like this, with a lot of flexibility, and you don't require, significant different types of equipment or large crew sizes to execute.
I think that last point is so important, that we don't need that significant equipment or crew sizes. Sometimes I find there's this misconception with advanced building technology, or these kind of big buzzwords of build better, build smarter, building technology, that they're not always accessible to crews on the ground or the people who are actually putting the structures up. I think that's something that's really cool about a panelized prefab system, is it is accessible. Again, we're saying this, but in the middle of Split Lake, Manitoba, where you can see there's nothing but trees around it.
Totally. And especially when that season to complete it or weather is so harsh, right? You have a small window. You need to find a way to execute quickly.
Absolutely. We've kind of alluded to this, but I think this is a really important point to underline. This wasn't a fireproof building. It was a fire-resistant envelope. And that distinction really matters when we're thinking about how we build better. Can either of you help us unpack why it's so important to use the right language? Fireproof versus fire-resistant versus fire-resilient. And what does that mean for designers and builders making spec decisions?
Yeah, for sure. Going back to the beginning, mentioning it, there's no such thing as a fireproof building, and I'll argue that with anybody later if they want, because I know some people, concrete building. It's the resilience of it. If it's heated for long enough, everything will either catch fire or unfortunately degrade to a point that it's just not safe. So going back to those priorities of life safety, property conservation. In this case, using the right materials, using us, and I love this picture for the reason that you can see it's a full SIP envelope in this case. We have some skirting panels at the bottom. You can see this was done on screw piles with beams. We have a SIP floor, walls, and roof. We used our tech panel on all of those elevations to seal it up. Seco chose some great windows and some great glazing for this as well. And so, this one is still under construction, so we have some openings, but you'll see, in I think, some photos coming up, and maybe a couple we've already seen, just how this building is completely sealed. And although it looks aesthetically very pleasing, I think it's actually a great, from an architectural standpoint, looks really good. There's no nooks and crannies. There's no, everything's very resistant to the heat of a fire. I don't know, Blain, did you want to add anything?
No, I think the only thing I'd probably add is like a lot of these things, like not fireproofness, but fire resistant is dictated by international and national building code, right? And so on top of what Russ said, ZS2 has invested heavily in that third party testing to support that the proof's in the pudding, literally. So that's important to understand as well.
I think I want to take a pause here. Up until this point, we've been talking about resilience in such broad strokes, like the science behind fire, the materials, how it all comes together as a system. Now, I want to get really into the weeds on the spec for this specific project, because at the end of the day, we keep saying this and we will keep saying it. Resilience starts on paper, and if it's not in the drawing or the spec, it won't make it onto the job site. So let's break this down. Blain, can you talk us through the details in the spec that make the difference here? What should an architect or builder be asking for if they want this level of performance for a full SIP roof? What's the difference between those thicknesses and insulation types?
Yeah, absolutely. And once again, situationally based, and what I'm going to explain isn't mutually exclusive. That's one of the good things about the tech panel system. So you'll notice between roof, walls, and floors, we got some variance, right? So roof thickness and floor thickness are both 10.25 inches thick, right? And they're both using a Type 1 EPS. Where that becomes relevant is with that thickness and that type of expanded polystyrene, which is the insulation that's in the center of the panel. We have an R value of 38.45, right? So for this situation, we knew we had to hit a minimum R value of 30, okay? And everything up from there, just based off the environment that they're building in, remote, cold weathers, all those types of things. So that was one of the big reasons as far as that, as well as structural capacity, things like that. But then on the wall, you'll see, okay, we're 6.5 inches thick, so we've shrunken that footprint, but we're still hitting that R value of 31. How are you achieving that, right? So in this specific situation, the architect and the builder, they specified a graphite foam. So a higher R value per inch, so better thermal resistance per inch in a smaller footprint. So, you know, they knew that they had to execute a specific metric on this build, and that's how they chose to do it. And there's tons of flexibility. But on top of that, they needed that thermal performance and overall envelope. But they're also in a situation where it's remote, they have limited labor, and they have a really small cycle, or they have to, you know, build against the elements, which they did clearly on this build. You can see by the snow on the ground. So that's kind of how I would dive into that.
That was great. Russ, is there anything you want to add?
Well, maybe. So it's funny because we get asked quite a lot by clients or people that we tour here in Calgary for a really efficient wall. And so we had somebody in the building the other day, and they asked for an R50 wall. And so we kind of smiled, and I was like, well, why? What are you looking to do? And there was an assumption, oh, I need the biggest R value possible. I need to make this building efficient. And what's interesting about tying it to Blain and even this building here is we love to educate people, and we do that through our tours, through our, like Blain, you know, being on site supporting right now. We love to educate them because it's not quite that simple. In this case, literally, if you had an R50 wall, not that say even R31 was their goal, like you can see here, and they wanted to use regular foam, that's going to be a 2x8 or 2x10 wall, and you're going to get to a point that you lose your building walls are so thick, you have problems with your windows, problem with the sills of your windows, you lose so much of the floor space of your building. There's diminishing returns. So where's that efficiency? The graphite foam in these walls kept them at 6.5, gave them a better R value, which, to be honest, with our panel, the overall rating on that building, because those lumber splines are out further, is actually increased compared to standard stick frame construction at 24 on center, let's say. So you're actually getting even a bigger increase without a really thick wall losing floor space. Imagine those buildings, if those walls were in 3-4 inches on every side, you're losing a lot of floor space. So it's a great way to maximize the building space for this particular client and give them a very efficient building that's going to be very inexpensive comparatively to run through the different seasons. So not just winter like we see here, but also in summer for cooling. And I think that's really important to note.
So Russ, you've been chomping at the bit to want to call out Seco and all the great things that happened with the execution here. They really turned the system into the real world resilience from the final finishing touches. What are all the layers that went into making this a fire smart strategy that you can both see in this picture or beyond?
Yeah, for sure. I appreciate you smiling at this one because I think you know how I kind of geek out about this stuff. Uh, Regardless of our panels, a picture like this shows how Seco knowing this is in a very remote area. It's really not a matter of if but when. Unfortunately, nowadays for fires, not just in rural or not in areas like this that are pretty remote, but even urban centers. We've seen that lately. This was built very smart. So you can see in this picture, they've used a metal siding, the vertical siding, and you can see just a bit of the standing seam metal roof that's used as well. By virtue of the design, there's not those nooks and crannies and places things can get into. Also using, because it's on piles. I mean, they're up. I don't know if they're in the permafrost exactly, but screw piles with beams, very smart way to build in that location, very quick and resilient. But they've skirted, using our panel, skirted that underneath, again, to continue that envelope. So it's a continuous envelope all the way up with fire resistant material. Compounded on that would be, you can see they're building it right. They've got high performance windows. They've got the right kind of HVAC units. This is them just as they're heating it in the winter, finishing it out. And I'm sure I'll be corrected at some point, potentially by any of the Seco people on the call. But they used the right stuff to make it very resilient. Even the windows they used, I might be getting ahead of myself here, but there was as the fire came through, there was an issue with one window. I still haven't confirmed whether it was left open or whether it failed because of the heat, that radiant heat and all the wind. But smoke damage was all the insurance claim was for, a little bit of smoke damage. I've had a bunch of insurance conversations lately, and again, sorry if I'm getting ahead of myself, but the insurance company was shocked that the claim wasn't bigger on this building, is what I've been told. Because the building itself performed extremely well. There was a little bit of smoke damage, a little bit of remediation. And so they were still able to turn this over and not have to do a full rebuild, not have to demo part of the building, throw those materials away, order new materials. They were able to keep all the original materials, which I think is a testament to not only Seco's design and choice of materials, but our product and everybody else that was involved in it.
Blain, is there anything that you wanted to add of, this whole strategy being built in layers? As much as I think all three of us are so proud of ZS2 and, the magnesium cement technology, we also prioritize building better and acknowledge that resilience isn't a single product. And it's unfair if we try to overstate that claim. It is that strategy built from layers. Is there anything you wanted to add onto like Russ's comments there?
No, I think you kind of said it, but really it's just those small details all stacking up, right? Like ZS2, we're only one component of a build, whether it's here with Seco or what I'm doing here in Jasper with High Rock. Like, it's all those choices add up, and choosing the right finishes and designs, they play a big part.
Love it. Yeah, being able to, support the entire exterior envelope with that floor, wall, roof system. And then, like you guys keep saying, it's those stacking of protections. So, we've talked a lot about this build, just keeping an eye on time. Can we talk about some broader lessons that we've learned here? And then how can we apply this to any project moving forward? We've talked about some key things. So to either of you, please jump in at any point. We've broken this down into 5 components. So these aren't theories. These are things we saw tested in real time at Split Lake, and their takeaways you can apply on your own project. So lesson 1 is really simple. Stop wrapping buildings in fuel. A lot of conventional assemblies stack combustible layers. The MGO didn't. Blain, Russ, anything you want to add in there?
Yeah, I'd say really quick, just because I have some experience with this. It's like the using vinyl siding in urban centers, typically on homes. It's very inexpensive, But once they realized, well, wait a minute, you're wrapping your building in fuel, unfortunately, the first line of defense was, well, let's put another layer underneath it so the building doesn't start, not remove the fuel. And so then code went, put a type X drywall or something non-combustible behind the vinyl siding. And just that thinking process, although that did help, it is wrong. We shouldn't be putting the fuel there in the first place. We should be building with smarter product. And that doesn't always mean more expensive product, but we need to be thinking, what's the lifespan of the building? What's the true cost of wrapping our buildings in products that don't make the most sense? And this building is a great example. Might have cost a little bit more upfront, but the building will last 50 years plus.
You know, we like to say a lot around ZS2 that the most sustainable building is the one you don't have to rebuild. And I think, you know, that starts at the beginning.
Absolutely.
So, lesson 2, ignition risk lives in the details. We've heard that fire will exploit those gaps, edges, any type of penetrations. We have to choose materials and assemblies that defend the structure. You know, embers don't really care what a spec says. They'll look for anything that can catch, melt, drip. Anything you two would like to add onto that lesson we can take away and apply onto any project, or specific materials?
No, I think you said it perfectly, but really it's eliminating any of that fuel. And if you look at traditional sheet goods, primarily OSB and plywood, you compare that to the tech board or magnesium sheathing that we can provide, and all of a sudden you have something that has tested zero flame spread, smoke spread index less than 5, to get really nerdy. But that is a resilient material that provides the exact same solution, that same structural performance that, you know, a fire rated gypsum does not, while still, yeah, structural, fire resistance, and, you know, a 3-in-1 envelope when you put it in a panel.
Moving forward, closing in that structure can quickly protect against that ignition and that fire spread. The faster you close, the less chance fire or weather has to exploit your building. That came from that panelized prefab methodology. If someone isn't using panelized and just trying to put this onto their own site, is there anything you guys could recommend or suggest of prioritizing that early enclosure?
Yeah, I mean, I'd say the comment here is perfect. When's the building most vulnerable? Whether that's fire, moisture, all the things. When we build the spaces we live in, what are we really doing? We're defending ourselves from the elements, you know, the outside world, let's say, and trying to control what we can to make our lives more comfortable and to be able to live. And so its most vulnerable stage is when the building doesn't have a roof yet, the windows aren't in yet. You've maybe in traditional construction, you've just got wood stick framing exposed. And that's one of the reasons why insurance is so expensive during that build, is because it's most vulnerable. So if you can use a system that gets you to a sealed envelope quicker, just by virtue of that alone, you're going to be better off because your vulnerability is less time.
Lesson 4, building on that strategy of resilience, layer safety with that defensible space and detailing. We've talked how those fire resistant materials are critical, but they're only one layer. Anything else you can add into that layered safety, Russ or Blain?
Yeah, like I think as far as like that layered safety, we go down to that raw component. Of course, we have something in our panels like an expanded polystyrene. So the center portion of it, of course, that is a flammable material. But we're taking that one step further, and we're controlling the other 2 variables, similar to what we said in the last point, right? We're encompassing that or enclosing it completely in a non-combustible sheathing, right? And then we're pairing that with airtight construction, eliminating more of those variables. Russ, do you have anything to add?
That's great. Actually, this was
Yeah.
a question we have. I'm going to jump a little ahead, but somebody entered this into the Q&A and brought it up. You mentioned EPS. That is not fire resilient. And can you expand and just be really clear? I think that's such an important point, that you're right. EPS isn't fire resilient. How did it work on this build? Russ?
Yeah, so I mean, yes, call it what it is. EPS on its own, if you put a flame to it, it will off gas enough that it combusts pretty easily. When you encapsulate that in a system like ours, and I witnessed our fire tests for our that Blain mentioned earlier, like the third-party testing. The nice part, when you spend that much money on third-party testing, they usually set up a live webcam and you get to watch it happen. So I've watched our panels through the 1 hour, 2 hour structural, non-structural, all this testing. And what struck me, certainly when I first got involved with these panels and even ZS2, was that as soon as the heat was put on, the panel doesn't just combust. The EPS doesn't just combust. Okay, well, why doesn't it combust? You're encapsulating it in 2 layers of an extremely fire-resistant material. Like we said earlier, nothing's fireproof. So these panels, if there's enough heat for long enough, will that insulation start to degrade to a point that it's doesn't hold the same R value? Absolutely. We don't make a claim that our panels are fireproof, but that takes a lot of time. And during that process, it doesn't burn. It doesn't openly combust. It doesn't. It's not like a piece of open EPS wood. It's enclosed between 2 really cool layers of fire-resistant material. So important to keep that in mind.
And then finally, lesson 5, and really the most important one. This project has shown us fire resilience isn't a feature. It is a responsibility. We've said this a couple times now, but you can't stop a fire from coming, but we can stop it from turning a building and structure into fuel. Resilience is about making those responsible choices from design and spec book all the way through to execution on site. Blain, Russ, is there anything you wanted to add on being this most important lesson, what you're seeing in construction, or why this seems to be so hard for people to think fire resilience is a feature, not that responsibility?
Right. And I think it goes back to having those readily available solutions that don't deviate from the path of, an easy install or an easy solution. And I think that's something we can really provide at ZS2. But more than anything, and I know Russ will attest to this, and you as well, Tyra, but ZS2, we're an open door. We want to help educate. We want people to come in, get their hands on the material, understand it more. So if you see an opportunity to capitalize on that and further your education, whether it's with our product or another, we're happy to be part of that journey.
Couldn't have said it better myself. Russ, anything you'd like to add there?
Similar, and we've noted it a couple times. It's not a one-time, okay, check the box. We've checked about how to make this resilient. It happens at every stage. Quite often, it's not talked about early enough. Design, even pre-design. What's the concept? Somebody comes with an opportunity. We would like to build a building in an area, and it doesn't have to be just an area this remote. We're seeing more of this everywhere. It can be urban centers as well. You have to be thinking about it every step of the way. So everything from design, pre-construction, construction phase, in this case, literally before the building was turned over, still thinking about it, having a very defensible space, defensible products, but also the way we live in our buildings, the way we maintain our buildings, the way we retrofit our buildings, that it doesn't stop. We have to always be thinking about this resiliency. And I think that's really important to keep that in mind.
Final note, I think just bringing this back to ground level, we've talked about these 5 lessons. We've repeated intentionally, but for the visual people out there, myself included, going back to this aerial footage, do you want to point out exactly kind of how this project checked the boxes of those lessons learned so we can connect those lessons to a visual example there? Russ or Blain, feel free to just help summarize and wrap it up here.
So I'll start off really quick. Literally to the points you have on this slide, it's quite easy. The materials used, if you look at that building there, you cannot, certainly from this angle, and I realize it's a bit far away, but I've also seen several videos closer up to the building. There's nothing scorched, nothing's burned on the building. Look at the roof; it's still perfect. It looks like the fire was like, whoa, hold on, we'll just go around you. That's what you want. The air tightness, literally there was one spot, that one window. So the air tightness, smoke wasn't able to get in, the heat wasn't able to get in. layered defenses, 100%. Look at the area around this. There's a program in most every province, and I think it's North American wide or worldwide, called Fire Smart, and it's all about, and it teaches people, don't stack the firewood next to your house. Well, in this picture, what do you see? You can see where the site office was, away from the building. You can see where the equipment is in this case, and I realize stuff probably moved. This was taken after the fire went through, obviously, but you can see that those fuels and any of those possible sources of or fuel sources of combustion are all away from it. They've defended the site quite well. So there's pretty smart layout in this one.
Blain, anything you'd like to add here?
No, I think, like Russ said, it's really another good chance to shout out and give some credit to CECO for doing things the right way, as far as removing all combustible materials around the building with the right substrates. And capitalizing on a system that allows for a clean job site, right? All of those things.
Awesome. Okay, so we will get to Q&A here shortly, but what's next? We just talked at length of behind the build, then some lessons we can do. What's next? First, put your materials to the test. Put them in your hands. If you would like, we are more than happy to send samples so you can cut it, test it, torch it yourself. That really is the best way to see the difference compared to conventional materials, whether that's an MGO panel or any other fire resilient or high risk material you're using. Second, we really encourage you dig deeper. For this one behind the build, we've got case studies, we've got full technical fire rated assemblies, photo documentation, testing reports, all ready to share if you did want to go beyond what we covered today. And most importantly, put this into practice. Build better, build more responsibly. Before we move into Q&A, Russ, Blain, anything final you wanted to add into what's next? We've wrapped it up.
No, I mean, I guess in kind of that sort of closing mentality, big shout out to everybody that had a hand in this from the beginning, from design phase. So whether it's from our project management team, CECO's project management team, designers, engineers, everybody involved, up to literally the people that were on site when the videos I've seen were literally trucks driving into site, fire is there, they're making sure people are safe. A shout out to all those people for doing what they did. I think the building, if you see those pictures now, that's a testament to everybody that was involved.
Agreed. Thank you. Q&A. Okay, I'm going to get into this first one. This is from Mike. Based on the performance of this project, can we make any assumptions how an urban project would perform in a fire scenario?
Yeah, I think it just boils down to, those details stacking up. So, in urban centers, a lot of the time, the sheathing requirements on zero lot line, all those types of things are non-combustible or have fire rated assemblies. Because of the amount of testing that we have completed, we can provide solutions for all of those things. And with that, you're using this exact same principles in the prefab solution that we can provide that will perform the exact same in different types of exposures to, whether that be fire, heat, and then on top of that, water, mold, pests, everything else. So it should perform exact same.
Then there's another one from Frank here. Why was Tyvek used as a WRB? Can MGO panels not act as the WRB with the joints taped? Where's the air barrier / air control layer? That's a great question. We get this all the time. Blain, do you want to start this one?
Yeah, so the panels themselves are not a finished product, right? And that boils down to local code authority having jurisdiction. You have to meet National Building Code. So the MGO, it performs extremely well in moist or wet environments, but it is porous. It can take on water. And so that's why you need that exterior weather barrier. And that's dealer's choice. If it's code compliant, typically it can be used with our system, and we're happy to help interface there. And then moving on to the vapor barrier portion of that panel, we do achieve a vapor barrier at the center of our panels, but because we have lumber at 48 inches on center, we do require vapor barrier tape or an approved vapor barrier at those locations. And once again, we've went out and we've got the third-party testing to support that.
That was great, Russ. Anything else you want to add?
No, maybe. I believe on this one, and this is something that Seco could speak to, and certainly our project manager, Gary Borick, on it. They actually used for the vapor barrier, I believe, tape throughout because it's a full SIP envelope. So the floor, the seams are taped, the wall seams are taped, and the roof. That was the interior vapor barrier, which speaks to what Blain said, where our panel meets that code, but it's how you connect everything. And yes, we've got a lumber spline, so by using a seam tape, it's a very efficient, inexpensive way to get that vapor barrier and making sure you meet the codes needed.
That's great. I have another great kind of technical question from Frank here. Do you offer composite splines made out of smaller MGO SIP or just the back-to-back wood stud splines?
Yeah, so right now, at this moment, all our third-party testing is based off of the wood stud or some other substrates, but composite isn't something that we're fully tested on at this moment. Doesn't mean we won't be in the future.
Great, thank you. Someone was asking about cost, just in general. There had been mention that it can be a little bit more expensive. Russ, can you talk a little bit about the cost of the overall kind of construction life cycle and then also just the material? What would people expect if they are ready to put this on their site tomorrow?
For sure. Obviously, construction, so you try to figure out apples to apples. Barring that for a moment, our product compared to, say, stick frame construction and the different components that are needed to get to that apples and apples comparison, a little bit more, 5% more cost than traditional. But when you start to factor in where the insulation is part of it, less lumber, the operating costs of that building over time, the speed of construction, reduced insurance, reduced skill for the installation of it, you start to realize really quick that in almost every case when I've been part of some evaluations, we are cheaper than traditional construction with a better finished product that's less money to operate that building over time. So important to keep those things in mind.
That's great. Thank you. And then I just have a couple final ones about, will this presentation be available to review later, or how do we get our hands on some of those specific certificates or testing? So I can take this one on. Yes, absolutely. We will deliver it to you straight in your inbox. We'll also put a link if you would like to learn some more. We'll make it really easy to reach out to us. We can accept carrier pigeons, emails, phone calls, DMs, whatever you need. We're here to help and support. And then for the actual certifications and testing, they are all public listings. So you can find them on the website or on our third-party agencies. So, for Tech Panel, what we talked about today, Blain, please feel free to jump in at any point, but we have a range of testing from full environmental product declaration, where we got a full life cycle analysis, to our ESR number with ICCES evaluations, to where you can see those specific kind of nitty-gritty data components of the flame spread index and moving forward. Blain, is there anything you wanted to add on like testing or certification?
Yeah, no, and then a little bit more relevant for Canada as well and the US. We have multiple listings through QAI laboratories as well. And if there's something on those public listings where you're like, hey, what about this? Seems like low-hanging fruit. There's a good chance we have that as well. So you can reach out to myself, the main line at ZS2, anybody, and we'll make sure that the relevant testing gets in your hands.
That's awesome. I can see a chat just went up from someone on our ZS2 team, Candace. Thank you very much. But yes, if anyone wanted to get a hold of Blain, Russ, myself, anyone, we put a link in the chat there, or please feel free to reach out. We're happy to support. We are coming up on time now, so I think if there's anything we wanted to add, Blain, I know you are ready to jump back on site. Thank you very much for your time. I'll leave it with, is there any final thoughts from you two?
No, I think for me, it's just credit to Seco and the ZS2 team, and a very specific and special shout out to Gary Borick, who's the PM on this project, because I know he blood, sweat, and tears from start to finish, and is a big reason as to why it was so successful.
We love you, Gary, very much.
I would echo the same thing.
Great. Well, thank you very much, and expect an email from ZS2 in your inbox shortly.
Thanks.
Awesome.
Bye,
Thanks,
everyone.
everybody.